Good afternoon. Welcome, everyone. My name is Lauren Culler, and I'm a faculty member in Environmental Studies and at Dartmouth Institute of Arctic Studies. And I have the honor today to introduce our speaker, Dr. Don Perovich. Dr. Perovich is a professor at the Thayer School of Engineering. He's an incredibly accomplished, internationally recognized sea ice expert and geophysicist. Dr. Perovich is the co-lead for sea ice research on this Mosaic project, which probably many of you have heard about. Mosaic is the multidisciplinary drifting observatory for the study of Arctic climate. And in fact, I read an article that described it as the largest polar expedition in history. It involves over 600 international partners from 17 different countries, and it actually just started a little over a week ago. The goal of this is to have scientists on a vessel that gets locked in the sea ice flow for an entire year, making important observations of Arctic climate, probably a lot of what we'll be hearing about today. So Dr. Perovich, in addition to being a sea ice expert and geophysicist, is also a really gifted educator and science communicator. I first met Dr. Perovich in a course here at Dartmouth called Intro to Polar Systems, when he explained to a very interdisciplinary group of students the technicalities of his sea ice research, really helping us understand some of the key concepts like ice-albedo feedback, and also weaving into it his rules for working in the Arctic, some of which we may hear about today, and if not, we should bring that up during the question and answer period. So just want to mention also that after today's seminar, immediately following, there's a reception upstairs in the Dickey Center, and everyone is invited to come up, join us, and continue the conversations with Dr. Perovich about sea ice. So I'd like to turn it over to Dr. Perovich to give his talk, In the Drift Track of Nansen, Exploring the New Arctic Ocean.
The Arctic Ocean is a harsh environment. Months of unrelenting darkness, bitter cold temperatures, high winds, blowing snow, shifting ice. Trust me, it's a harsh environment. The Arctic Ocean is frozen. It's so cold in the Arctic that the ocean freezes, forming sea ice. This sea ice cover is vast in aerial extent, covering millions of square kilometers. But it's just a thin veneer of ice, only a few meters thick. And since it's floating, it moves. Driven by winds and by currents, it can easily move kilometers per day. And we can look at it and see it's bright and it's white. It's highly reflective. The Arctic Ocean is also a place of dreams, a place that's always captured our imagination. And it's a place of dreams now, and it was a place of dreams long ago, more than a century ago in the 1800s, where the Arctic grabbed people's imagination with dreams of the unknown, questions of what lies in the heart of the Arctic. No one knew. Was there a continent there? Were there islands? What was it like? Was there an open ocean beyond the ice? And that motivated many explorers. And you've probably heard of some of them, explorers like Franklin and the Lost Expedition. There were many expeditions and so much suffering. And just looking at one of those expeditions, it was the voyage of the Jeannette. It was the first major US Navy Arctic expedition. They set out with a goal to get to the North Pole by going up through the Bering Strait into the Arctic. In September of 1879, they were frozen into the pack near Wrangel Island. They didn't know it at the time, but that was really a bad place to be. There was a lot of ice activity and the ice broke up. And they drifted for a year and a half, until June of 1881, when the ship was crushed in the ice. At that point, they tried to make it to safety. There were 33 people. They had some lifeboats. Of those 33, only 13 survived. The rest were lost at sea or starved once they reached land. So that's the voyage of the Jeannette. It was similar to a lot of the other early explorations. But there was one more thing about it. And that's years later, in June of 1884, 3 years later, wreckage from the Jeannette was found in the ice off the southern tip of Greenland. Now, people wondered how it got there. And one person in particular, Hendrik Mohn, had a theory. Mohn was a very respected scientist. He was an astronomer and meteorologist. In fact, he founded the Norwegian Meteorological Society. And his theory was there must be a current. There must be a large-scale current from east to west that brought the ice down and brought the wreckage of the Jeannette. Well, as I said, he was very respected, but nobody was buying this idea because at the time the belief was the Arctic Ocean was shallow, because it was certainly shallow around the edges. And if it was shallow, there must be a lot of islands. And if it's shallow with a lot of islands, there can't be a major current such as that. So in general, he wasn't really listened to, with one notable exception. A young, recently graduated PhD listened intently and had an idea. And that was Fridtjof Nansen. Nansen was a neuroscientist. That's how he got his PhD. He was also a polar explorer and had recently done the first crossing of Greenland, and an oceanographer. Much later in his life, he became a diplomat, a humanitarian, and a Nobel laureate. Now, if people were skeptical of Mohn's theory, they totally didn't believe that Nansen could do this. Even though they were respected his accomplishments, the idea was, this is crazy. But they did say, well, we've learned a lot about the Arctic, and Nansen's very diligent. He can learn from that knowledge. We've learned that we take an existing vessel and refit it. And we never, ever get trapped in the ice, because when you do, bad things happen. And if we can navigate through the ice, we can get to the open polar ocean and take lots of people, because you're going to have some casualties along the way. And Nansen looked at that and considered it and decided to reject every single item, decided this was all wrong, and he came up with a new paradigm. Rather than refitting an existing ship, he was going to build his own ship from scratch, designed to be in the ice. He planned on getting trapped in the ice and then drift to the pole and then out through the North Atlantic, just like the wreckage from the Jeannette. And take a small team of well-trained men that were used to working in the Arctic, and learn from the Inuit. After his crossing of Greenland, he spent several months in Nuuk waiting for his trip home. And he thought, well, this will only take a few years, or maybe 4 or 5, but don't worry till 7 or 8. And it was an audacious plan. Well, that was the nicest thing you could say. It was audacious. Some thought it was outrageous, an insane plan. Now, the key to this was a ship, and that led to the polar ship Fram. In Norwegian, Fram means forward, which is a very apt name for this ship. It was a totally new ship design. It was based on a 3-masted schooner, which was double-ended. That means the stern had the same shape as the bow. You can see it in the diagram here. It was unusually wide and shallow. It was squat. It was 39 meters long and 11 meters wide, and only had a draft of 5 meters. It had a rounded hull with nothing to grip. You can see it in the cross sections. In fact, the naval architect that designed it, Archer, said the design was such to slip like an eel from the embrace of the ice. The idea was when the ice pressures inevitably came, rather than crushing the ship, it would just pop it up on the ice. Now, it still had to be strong enough to withstand some forces, and so it had a hull thickness that on average was 2 feet 4 inches thick. And at the bow and the stern, it was even further reinforced with 4 feet of wood. And it had a crew of only 13. And this shows the drift of the Fram. It took Nansen a couple years to organize the expedition, to get funding for it, to have the ship built. And so they were ready to leave in July of 1893. They left civilization, as it were, in Vardo, Norway, on the 21st of July. And from that point on, there was no communication with anybody. They voyaged up the northern coast of Russia, and this was not an easy trip. This was literally a voyage between a rock and a hard place. It was in shallow waters, and on one side was land, and on the other side was the encroaching ice cover. But they finally made it to where they wanted to start. They were frozen into the ice on the 22nd of September, 1893, and they drifted for a year, then a year and a half. And finally, Nansen realized that while they were drifting kind of the way they expected to, they were going to miss the pole. So he decided to have a mad dash to the pole with one other person, Nansen. They got their skis on and they headed off to the pole. Now, when you're skiing on the ice, how much progress you make really depends on what the conditions are. If you're lucky, you can cover maybe 10 or 20 kilometers a day. The ice can move 10 or 20 kilometers per day. And if it's moving the same way you're going, that's great. If it's moving in the other direction, it's not so good. And finally, after a month of doing this, Nansen realized they weren't going to make it to the pole, and if they wanted to survive, they had to start heading back so they could reach land before the summer melted the ice. They did reach 86 North, which was the furthest north that anyone had ever reached. They did make it to land and started working their way back. The Fram continued drifting, and it drifted for a few more years, and on the 13th of August, 1896, it was released from the ice. And incredibly, around the same time, Nansen was making his way back to Norway. He had hitched a ride on a ship. And there was a giant rendezvous on the 21st of August in Tromsø, where Nansen and the Fram were reunited, and they worked their way down the coast to Oslo, where they arrived on the 9th of September to a celebration that was the biggest in Norwegian history. This was an incredible expedition, 3 years across the Arctic. Now, they learned a lot from this expedition. They learned indeed there was a drift pattern, and the drift was close to what they expected. Another thing they learned was while the Arctic Ocean was shallow around the edges, it was really deep in the middle. It was so deep they didn't have enough chain to measure how deep it was. They learned that the Fram worked. When the pressures got great, the ship was popped up on the ice, and they gained weight. They showed that a small team, well supplied, could also live off the land and do just fine. Now, this was mainly motivated by exploration, but it was more than that. Nansen was a scientist, and science was really important. And this expedition produced 6 volumes of scientific findings with information on magnetism, meteorology, oceanography, and sea ice. It was just an incredible voyage where they learned so much, not just about geography, but about science as well. The Arctic was in their dreams. And even today, the Arctic is still in our dreams. Slightly different dreams. Now we have dreams of present and future climates. Maybe dream's the wrong word. Sometimes it feels like we're having nightmares of present and future climates. And what's shown here are 2 maps. Not a map with blank spaces, but maps of temperature. Temperatures in the past, the present, and the future. In this plot on the left, we see the change in temperature over time from 1960 to 2010, where it goes from the North Pole through the equator down to the South Pole. And these are observations. These are observations that we've made over time. And what you can see in early years, it's a little bit warm in one place, a little bit cold somewhere else. But in recent decades, the picture's changed. There's more of these yellows and oranges that show warming. And when you look at it, we see the greatest warming has happened in the Arctic, where we've observed temperature increases of a few degrees centigrade just in the past 2 decades. On the right, we see a map of not what is, but what might be. It's a map using climate models to look ahead to the year 2090 and see what the temperature change would be under business as usual. And here you see everywhere you look, there's oranges and reds. Everywhere you look on Earth, there are increases. But it's important to note that the deepest reds and the purples, the largest increases in temperature occur in the Arctic. And that leads us to another attribute of the Arctic. The Arctic Ocean is fragile. Sea ice is a material that's always close to its melting point, and it's very sensitive to changes in temperature. And we can use that. We can use Arctic sea ice as a proxy for changes in temperature. It's an indicator of climate change. If you think about it, if it's getting colder, we would expect there to be more and more ice. It's this large, thin veneer. And if it's warmer, we would expect there to be less and less ice. So we can use sea ice as an indicator of climate change. And we're fortunate because for the past 40 years, we've had satellites looking down at the ice cover day and night, good weather, bad weather, detecting where there's ice and where there's open ocean. And from that, we have a 40-year record of what the extent of the ice cover is. And we can look at that record, and we see this plot. Basically, on the vertical axis, it's the ice extent in millions of square kilometers. On the horizontal axis, it's time, from 1979 up into the present. We now have a 40-year record of this. And each dot represents a month, and you look at this and you see there are these wild oscillations, almost by a factor of 2. And you're thinking, wow, we've got some good science here. This is going to be a great finding. Well, it's the seasons. And people have already discovered the seasons, so we're not going to get famous out of this. But it does make our point that we can use sea ice as a detector of change. Because in the winter, it's cold, and the amount of ice goes way up. And in the summer, it's warm, and the amount of ice goes down. This plot also illustrates a problem that we have trying to detect a climate change signal. Because what we have are large seasonal variations and variations from year to year. How do we tease out a relatively small climate change signal from those larger variations? In the case of sea ice extent, we do it by throwing away a lot of data. Instead of looking at every month, we're just going to look at 1 month, and that's September. Because September is the end of summer when the ice reaches its minimum value. And that's when we'd be able to detect a change in climate the easiest. And when we do that, we get this plot. Again, same kind of plot, the ice extent over time. And the first thing you notice about this, there are a lot of changes. Things go up and down, they bounce around from year to year. Here in 1995, we had the lowest we had ever recorded to that point. In 96, we had the largest we ever recorded. So there is this large year-to-year variability. But if you look at this, you can also see there's a general downward trend. And we can look at that more closely just by fitting the best straight line we can through it. And that's what's shown here. When we do a linear fit to this data, we see there's a decrease of 13% per decade that we've seen over the past 4 decades. Now, when it comes to sea ice and climate change, this is truly the iconic graph. This has been looked at in incredible detail. We fit different curves to it, polynomials, exponentials. We've broken it up into little pieces. We stared at it like so many tea leaves. And people have come up with different conclusions from it. But the main thing is, no matter how you look at it, there's a decrease. And I have to confess, I've spent quite a bit of time looking at this, trying different things with it. And what I think is most telling is this graph right here. In 2007, we had the largest decrease in ice extent that we ever saw from September to September. It was the biggest decrease, and at the time, it set the all-time record minimum. Since then, there have been some ups, some downs. There was a new record set in 2012. But the key point is, we've never gotten back to the pre-2007 levels. That basically, we've entered into a new Arctic regime. This was a fundamental change in the nature of the ice cover. Now, these graphs are good. They're numbers, they're nice and quantitative. They give us an idea of what's going on. We can apply some math to it. But it's also good to get more of a feel for it, what these changes look like and where they're changing. And what I'm going to show now is an animation from NASA. And a couple of things to look at. It shows 2 things. It shows the extent of the ice, and it also shows a quantity called the age of the ice. Now, sea ice compared to glacier ice is really young. It can be only a few months old if it just formed that year, or it can be up to 4 or 5 years old. And what's shown in the colors, you can see the scale here, is the age of the ice. The ice in white is 4 or 5 years old. And that's important because generally speaking, the older ice is, the thicker it is. And the thicker it is, the more resilient it is. And that resilient ice can make it through a warm summer and smooths out the oscillations in the climate system. And so you can see here there's a large amount. Up here it actually tells you how much of this old ice there is. Back in when this started in January of '84, there's around 2.5 million square kilometers. So we're going to go through one of the things I like about it, it's almost as though the ice is breathing. It kind of inhales and gets bigger in the winter and exhales and shrinks down in the summer. And you can see that annual cycle, the ice moving around. And if you look at it, the old ice comes out here along the east coast of Greenland to a region called the Fram Strait. And yes, it's named after the same Fram. But we see as we go through, we still have this large amount of this older, thicker multi-year ice. It extends in the winter, retreats in the summer, and it's pretty much a solid unit. Sometimes it's round, sometimes it gets stretched out, and that's mainly due to what the atmospheric pressure patterns are in the winds. Now, as we get into the 90s, into the 2000s, you start to see some differences. There's some younger ice mixed in with the older ice. We're still outputting it here. And the ice in this area tends to go around in circles and get older and older. And as we get closer to 2007, watch this area. And so into 2008, and if you look at it, now we have streamers of ice going into this region and not making it out, just melting in place in the summer. As we come up to 2012, it's another record minimum. And now there's just small strings of this multi-year ice. It's down under 500,000 square kilometers. And the old ice is now being more or less restricted to just being off the coast of the Canadian archipelago. So that's just a visualization of how much things have changed over the years. Let's take a look at a couple snapshots to see the more detail. This is the way it looked in September of 1984, when we had quite a bit of the old ice in here, over 2.5 million square kilometers of it. And we had a graveyard. Ice was exported out the Fram Strait, but we also had a nursery in the Beaufort Jar where the ice would just go around and get older and older. We jump ahead to 2012, and now we've got two graveyards. The ice that flows into this area in the summer completely melts. So it's a large change. And one of the difficulties is putting these changes in perspective. I mean, looking at it helps some. And sometimes you'll hear, well, climate's always changing, there are always variations. Maybe this is just a fluctuation. So it's good to try to put it into some context. In September of 1980, the ice cover was roughly 7.8 million square kilometers. In 2012, it was reduced to 3.4 million square kilometers for a loss of 4.4 million square kilometers. Now that's a bunch of numbers, and the numbers are really too big to have much of an understanding of. So let's try to put it into a different context. It turned out that back in the 1980s, the ice cover was around the size of the continental United States. So we can just ask ourselves the question, between the 1980s and 2012, how much of the United States has melted? And that's how much. The entire US east of the Mississippi is melted. The band of states from Minnesota down to Louisiana melted. North Dakota, South Dakota, Nebraska, Kansas, and Oklahoma all melted. This isn't a fluctuation. This is a major change. And so we've taken a look at what's happened to the sea ice. But being people, we always want to know what's next. We want to know what's going to happen next in the story. And so for that, we turn to climate models. And climate models are interested in Arctic sea ice. And what you see here is a familiar plot, ice extent in the vertical axis and time on the horizontal axis. Only now, the time scale isn't a few decades, it's 2 centuries, starting back in 1900, going up to 2100. And this is the accumulation of results from a number of different climate models. The solid blue line represents the average of those models. Kind of the blue band shows the range of those models. And orange shows our observations. And there's a couple key points from this plot. The first one is reality is happening faster than the models. We're seeing losses at a more rapid rate than are predicted. And the second is the models have quite a bit of spread that only gets bigger as we go into the future. You know, the models, if we look at 2100, we have a range of outcomes to, we could have more ice than we have now, or we could not have any ice at all. That's not really a very satisfying answer. And if you talk to the modeling community, they explain that there's many processes that just aren't being treated properly in these large-scale climate models. And that the reason they're not being treated properly is there aren't enough observations. That we need observations to improve our treatment of these different processes. So we have a system that's undergoing tremendous changes. We've entered into a new Arctic. The modeling community says we need more observation, and that's the motivation for Mosaic, the multidisciplinary drifting observatory for the study of Arctic climate. It's a year-long drift experiment that started on September 20th with the ships leaving Tromsø, Norway, and will continue to October of 2020. The centerpiece of Mosaic is the German icebreaker Polar Stern, which will go into the ice, be frozen into the ice with a camp next to it and drift for the next year. Mosaic is guided by an overarching science question. What are the causes and consequences of an evolving and diminished Arctic sea ice cover? And under that overarching question, there are 5 sub-questions. What affects the heat and momentum balances of sea ice? How does first-year sea ice move and deform? What processes contribute to clouds and precipitation? And what are the cycles of ecosystems and biogeochemistry? And how are these ongoing changes impacting the Arctic system? Mosaic is about understanding the new Arctic, which has less ice and younger ice. So let's take a minute and do Mosaic by the numbers. It's the biggest sea ice experiment ever. It's highly interdisciplinary and it's international. Mosaic has undergone 10 years of planning. There are 19 nations involved. It's going to take 5 icebreakers to do it. Right now, the bill is at $150 million, and the costs haven't stopped coming in yet. It's involving 600 experts. Scientists will either be in the field or working back home. The overall duration of the expedition is 390 days. And of those days, 150 of them will be in total darkness. And the expected drift is around 250 or 2,500 kilometers. Now, if you're doing a big drift experiment like this, the first challenge is where to start. And that's what's happening right now. You know, I checked on the website before coming over. They're looking for a flow. Basically, we're shopping for a house. And if you're shopping for a house for a year, the first thing you want to do is decide what neighborhood you want to live in. Where do you want to start? And we worked on that quite a bit. We decided we wanted to start from the Laptev Sea, north of Russia. But we wanted to stay out of the Russian exclusive economic zone because we can't take measurements there. And we wanted to come out to Fram Strait, but not too soon, but not too late. And to take a look at this, We ran hundreds of simulations. Thomas Crumpin at the Alfred Wegener Institute ran hundreds of simulations using the best ice drift models available, also taking data from satellites and from autonomous buoys to come up with the odds of drifting far enough north or drifting into the Russian EEZ. And what's the survival rate? Not necessarily that the flow wouldn't break up, but that whole area would be nothing but water. And we use this to inform where we would start. And again, Nansen just had somebody's fanciful idea that there was an overall drift. And we have all of this information. Now, once you decide on the neighborhood, the next thing is, what do you want for a house? What flow do you want? Well, you want a flow that's at least 2 years old. You want a flow that's big enough, more than 1.5 kilometers across, and you want it to be thick enough, more than 1.5 meters thick. And you want to be close to the ice edge because we want to get this mix of old ice and young ice in open water. But you don't want to be too close to the ice edge because wave action can come in and break the flow up. And you want to be in a place where the drift forecasts are favorable. We're really looking for a Goldilocks flow here. Now, after all those calculations and all the discussions, what's seen here is the projected start point and the drift of the polar stern. It's color-coded by month. Here we are in October of this year, going through the whole year and coming out to Fram Strait October of next year. This is the hypothetical drift pattern. And if you look at that, it should seem vaguely familiar, or maybe not even vaguely familiar. There's Nansen's drift of the Fram. We're basically going in the drift track of the Fram. Now, there are a couple notable differences. We're starting much further north. And the reason for that is there's not ice anymore in September where the Fram started. We have to go significantly further north to find ice. And we also expect that our drift will only take a year, partly because we're starting further north, but also partly because this younger, thinner ice pack moves a lot faster than the old one did. Now, the Fram was on its own for 3 years. We're doing things a little bit differently in Mosaic. Mosaic will have 6 legs. The first leg is 3 months because it involves setting things up, but in general, the legs are 2 months long, and there'll be rotations done mainly by icebreaker. And right now, there are 2 ships heading north, the Polar Stern, which will be the drift ship, and the Russian icebreaker Fedorov, which will help deploy things and gas up the Fedorov before returning home. The rotation between legs 1 and 2 will be done by a Russian icebreaker, the Admiral Makarov, and it'll also do the next rotation between 2 and 3. Leg 4, the plan is to do it by aircraft, because at that point, it'll be April, we'll be near the pole, and in the dead of winter when the ice is at its maximum extent, we didn't feel that we could get an icebreaker up there, so that'll be done by aircraft. And then in spring, the Swedish icebreaker Odin will do a rotation, and then at the end of summer, the Chinese icebreaker Zhulong will do a rotation. So you've got 5 icebreakers involved in this. They'll be resupplying things, they'll be swapping out science teams. There were so many people that wanted to participate in this, but only so many berths, so the way was resolved by rotating people in and out. There's also an opportunity, the Polar Stern needs to be gassed up periodically. So these resupplies will bring in fuel for the ship, and it's also a chance to bring in food and other supplies. And from a scientific perspective, it's an opportunity to extend the spatial scale. While those ships are moving, people will be making observations, weather balloons will be launched, we'll be doing an ice watch to look at what the ice conditions are. Mosaic is interested in spatial scales. This is an incredible opportunity. We want to be sure we get it right. There's what we call the Central Observatory. It's basically the ship and around the ice around 5 kilometers out. You can think of it as how far you can walk. And that'll be the area where the intense observations are made. We'll be setting up instruments, will be doing things that you need a person to do. Beyond that, there's the distributed network. This goes on to an area of roughly 50 kilometers. It's designed to be the size of a grid cell in a climate model. And here we'll make observations with autonomous instrumentation that makes some of the measurements that we'll be making at the Central Observatory. And there'll also be aircrafts and helicopter flights. And finally, there's the large scale. This is a scale of thousands of kilometers. The resupply ships will look at this scale. There'll be long-range aircraft flights, and we'll get information from satellites. And this is also something that will be useful for climate models. And that's one of the really interesting things about Mosaic. It's really been unlike any experiment that I've been involved with, because since the very first day of planning, it was both the modeling and the observing community getting together to design the experiment. That basically we sat down and the modeling community said, here are the things that we don't understand well. Let's come up with a way to make measurements so we can improve our understanding of those items. And so really we've designed a virtuous cycle where we have models informing observations to improve models. Mosaic has 5 teams: atmosphere, sea ice, ocean, ecosystems, and biogeochemistry. And each of those teams has been meeting together to define what measurements they want to make, what their science questions are, how they're going to do things. And even more importantly, they've been working with each other to find common areas where we can get synergy between these groups. For example, if we take sunlight, the atmospheric scientists are interested in how sunlight interacts with clouds. From an ice perspective, we're interested on how the sunlight's partitioned. The ecosystem people want to know how much light reaches the ocean for primary productivity. And the biogeochemists have photochemical processes they're interested in. So it's really an interdisciplinary effort. So let's take a quick look through some of these different elements to see what we're going to be doing up there. For the atmosphere, it's clouds, clouds, and clouds. If you talk to anyone, they'll say, we don't treat clouds in Arctic models well enough. For that matter, we don't treat clouds in climate models well enough. So there'll be intensive study of clouds using ship-based cloud radars and cloud lidars. There'll also be aircraft overflights. There'll be studies of aerosols. And then there's also an interest in precipitation. How much snow do we get in the winter? Do we have rain events in the summer, or do we even have rain events in the winter? And of course, there's interest in what's going on in the boundary layer in terms of temperature, humidity, and wind speed. And there'll be a tower that's profiling those properties. There'll also be balloon launches looking at that all the way up through the atmosphere, 4 a day, and the results from those balloon launches will be incorporated into weather forecasts. And we're also interested in the surface energy budget, how much heat comes in, how much heat goes out. The ocean. In some ways, there's some similarities with the atmosphere. The atmosphere has a tower. The ocean has a mast going down, looking at profiles of temperature, salinity, and currents. There'll also be studies looking at turbulence at the ice-ocean interface and how much heat goes from the ocean into the ice. There'll also be studies looking at leads. Leads are areas where the ice is broken apart and there's open ocean. We'll be studying in the winter how heat is lost from the leads, and in the summer how heat is entrained in the leads. There'll also be deep casts in the ocean for sampling purposes. Rosettes of bottles will go down. These things are called Nansen bottles. And yeah, it's the same Nansen. Biogeochemists are really excited because it's a chance to look at sunrise. You have photochemical processes in an area where it's dark for several months on end. And then the sun rises and things start to happen. And typically it's very hard to get up in the ice pack at sunrise unless you're already there. And for Mosaic, we'll already be there. So they'll be looking at carbon, sulfur, nitrogen, and halogen. And they'll mainly be doing this through sampling techniques, sampling of the air, of the ice, and the ocean. And they're also interested in the amount of sunlight. and how that changes over the course of the year. And then there's ecosystem studies. Their main excitement is winter. For years, the thought was, well, we don't have to study winter because nothing happens then. But it was really more like, well, since we're not there, nothing's happening, right? So this is an incredible opportunity to really see what's going on in winter and to observe the changing ice ocean habitat. Now, the ecosystem studies are mainly focused on the bottom part of the food web, looking at ice algae, phytoplankton, and copepods. And they'll be looking at nutrients and light and trying to understand both the carbon and nitrogen cycles and looking at particle fluxes. And the way they'll be doing this is they'll be taking samples from those Nansen bottles. They'll also be doing net tows to get samples of what's in the ocean. And they're going to be doing some ice core sampling. They'll be taking, over the course of Mosaic, probably 2,000 or 3,000 ice cores to look at what's going on at the bottom of the ice. And then there's sea ice. We're going to take a little bit more time to talk about sea ice because that's the most exciting part. It's also the part that our team's involved with. There are 7 of us on the project. 4 of us are from Thayer. We also have 2 collaborators from the University of Washington and 1 from the National Center for Atmospheric Research. And we're looking at the ice. We want to look at the components of the ice. We want to see how it varies spatially and what its temporal evolution is. And again, just like Mosaic as a whole, our observation plan is motivated by the modeling community. Our modeler is Marika Holland at NCAR. She's told us what some of the holes and gaps in the models are. And one of them is snow. Just a simple question is, how much snow is there? And how does it vary spatially, and how does it vary over time? And then to look at more details, what are the grain size of the snow, the grain type, what's the density of the snow cover, what's its stratigraphy, and most importantly, what's its thermal conductivity? And we have devices to measure snow depth. We can measure thousands of snow depths in a day. We'll have temperature strings looking at temperature profiles in the snow cover. And we also, on board the ship, have devices to look at computer tomography, where we can take samples, take them back to the ship, and look at the very detailed structure of the snow. We're also looking at sea ice morphology. What's the surface topography of the ice? How thick is it? And then what are some of the properties? How big are the flows? What are the melt ponds like? And what melt ponds are, in summer, the snow melts and the surface of the ice melts, and some of that meltwater collects, forming these melt ponds. And they're very interesting because they have an impact on the freshwater balance and also on how sunlight is distributed. And we'll look at ridges, places where the ice crunches together. And again, looking at these leads. How do they freeze in the winter, and how do they enhance melt in the summer? And we have a number of devices to look at this. We'll be doing ice thickness surveys, both from the surface and from helicopters. And we also now have a high-resolution surface-based LiDAR, where we can get very detailed maps of the surface. And we'll be setting out areas where we'll map repeatedly, so we can see the snow build up in the winter, how it moves around during windstorms, and how the surface melts during the summer. We'll also look at the sea ice mass balance. It's my second most favorite sea ice property. And all the mass balance is how does the ice grow in the winter, and how does it melt in the summer? Mainly on the surface and the bottom, but also on the edges of the flows and in the interior of the flows. And for something this important, we use highly sophisticated instruments, ablation stakes and thickness gauges, which are basically sticks and wires. They're the same things people have been using for a century, but they're inexpensive, so you can put out a lot of them. We're going to put out over 100 of these sites where we can measure the changes in ice growth and also in terms of surface and bottom melting throughout the whole year on a variety of ice types. And we'll complement that with something a little bit more modern, the sea ice mass balance buoys that do the same thing as these thickness gauges and ablation stakes, only they add some other measurements such as temperature, and you don't have to be there. They send it back via Iridium satellite. And we'll be looking at my most favorite geophysical parameter, and that's solar partitioning. We're going to follow the photons and see where does all the sunshine go. We're going to measure how much sunlight comes in, what's reflected from the surface to the atmosphere, also known as the albedo, how much is absorbed in the ice, and how much is transmitted into the upper ocean. Now, on the face of it, that would be pretty easy except for two things. One, the spatial variability you see, and two, the temporal variability as you go from spring to summer. And we're going to take that into account by doing surveys. We're going to set up several survey lines, each a few hundred meters long, where we go along and we measure those properties. We'll also drill some holes through the ice so we can put instruments down underneath to measure the amount of light that's transmitted. And we're going to coordinate this effort with some of our German colleagues that have a remotely operated vehicle where they can do surveys under the ice as well. We're going to figure out where does all the sunlight go. We're also interested in sea ice dynamics. We want to measure the deformation of the ice. We know these ridges form. We also want to measure the motion of the ice. How does it move on a large scale and also on a smaller scale? And ultimately, we want to understand the mechanical properties of the ice. What's its rheology? And we'll do that through a number of different instruments. We'll have stress sensors that you embed in the ice and measure how much force the ice is undergoing. And we can see how much it takes to break the ice. We'll also have an array of GPS buoys that are part of the distributed network. We'll have 50 of these measuring very precisely the changes in ice position. And one of the really exciting things is we have a brand new LiDAR that can measure small deformation on very small scales. So we can see how the ice is deforming under pressure. And it's even possible that may give us an inclination if things are about to break up. So those are the 5 main things that the sea ice group is going to be looking at. And if you have an experiment where you've got 19 nations, 5 icebreakers, 600 people, you might expect it takes some coordination. And indeed it does. We spent a lot of time over the 10 years of planning, particularly the past few years, about figuring out how to coordinate this. And one of the examples is real estate. You'd think we're out in the middle of nowhere, ice as far as you can see in every direction, that why do you have to worry about real estate? Well, you do, because it gets used up really quickly. So we spend a lot of time coming up with zoning laws. What you see here is our idealized map of what reality is going to be like. And the grid, each grid cell is 100 meters. This has the ship parked next to a nice thick multi-year flow. And right next to it is some younger, thinner ice. And what you see is there's a power line that goes out through Ocean City out to Met City, another power line that goes out to an ROV area, power line that goes out to remote sensing. And when you're in the 700-meter circle, it's the safe zone. From 9 to 5 every day, you can work in that zone and not have to worry about polar bears because there'll be polar bear guards patrolling that whole time. If you go beyond that, there's a whole other set of protocols you need to worry about. There are also wilderness areas where we're going to try to stay out of those areas and you can't go into them without permission from someone. So we've really spent a lot of time coordinating real estate. And we've also spent a lot of time coordinating what we're going to do because nobody's going to be there the whole time. In fact, if you look at most projects, they won't even have people there the whole time. Our project, we have Ian Raphael on Lake 1 now, and we also have people on Lakes 4, 5, and 6, but nobody on 2 and 3. So somebody's going to have to do our measurements. So we sat down as a team and decided what are the key things that we want to see happen the whole year, and how are we going to make sure that they do happen. And so what we have for every leg, there's a schedule like this. This is a schedule, and each team has a schedule for each leg. This is the sea ice schedule for leg 5 from the middle of June to the middle of August when I'm going to be up there. And there's actually 14 people on the ice team, which is the most we'll ever have up on the ice. Summer is really an interesting time. And you can see a breakdown. We have people assigned to cores. Monday is ice coring day. We go out with the biogeochemists and the ecosystem folks, and we drill holes in the ice all day long. There's also time for stakes and transects and the remotely operated vehicle and ponds. A couple other features in this schedule. You see this red area for basic. And what that is, those are the basic things we have to do. Cleaning instruments, changing batteries, things like that. Also, each day, there's a person assigned to the helicopter, which in the summer usually means sitting around hoping the fog will go away. But we do have a fairly ambitious helicopter program of photography and surface LiDAR scanning. And there are these green areas, flex time. Got to have a little bit of flex in the schedule. And with that, the flex time serves a few purposes. One, there could be weather days, particularly in the winter, there are days where people just aren't going to be able to go out and work outside. And for the ice program, most of our program is out on the ice. So the flex days allow you to shift things around to accommodate the weather. The second thing is, while we've all agreed on some common measurements that we all think are important, everybody kind of has their own thing they want to do, and the flex time is an opportunity to do that. And then finally, we realize that Mosaic isn't a sprint, it's a marathon. And you have to build in some time so people can just kick back and take it easy. And the idea is Sunday mornings, let's just take it off, maybe do some laundry, read a book or something. So the flex time allows for that as well. Now, we're all excited about Mosaic. I think everybody has this vision of what they're going to see, what the results are going to be, the wonderful papers we're going to write, the unexpected things we've never dreamed of. But we all agree that the data is the legacy. The data from Mosaic, the hope is that this will be used 20 or 30 years from now. And because of that, we formalized the Mosaic data policy. If you want to be part of Mosaic, you've got to sign this data policy. And it's 12 pages long and basically says, yes, I'll share in great detail. So we're working to promote data fairness and accessibility. There's a major focus on observations to archive, to get the data in a secure archive as fast as possible. And with that in mind, there's 2 data scientists that will be on board the Polar Stern throughout the entire experiment to get things, at least the preliminary data, archived. The ultimate goal is to get a complete data set that's archived and published with all the explanations of what that data is. There's a really strong commitment to data sharing and archiving. When you look at it, Mosaic is a tremendous opportunity. It's an opportunity to spend a year on the ice, to study this young first-year ice, to perform process studies, to conduct interdisciplinary research with the team, to take that knowledge and improve models, to give us a chance for an improved understanding of the new Arctic. And we're all really excited about it. And if you want to follow Mosaic, there's a website that gives you, this website gives you updates where it is. That's where the ship was as of 2 o'clock. It's looking for a flow. And then there's the more general Mosaic expedition. We've been planning this for 10 years. It's almost surreal that it's actually happening. But people are on the ship now and they're looking for a flow and getting ready to deploy things. And it's really a very exciting experience. But I want to make one last point, and that's not just an intellectual exercise. These changes in the Arctic are having consequences today. They're impacting coastal communities that without that sea ice cover in the fall are exposed to coastal storms and having enhanced erosion. There's impacts on shipping as people start to look for shortcuts across the top of the world. There are geopolitical implications. Who owns the Arctic? Used to be an easy question, who cares? But now with the ice retreating and with surveys showing that over 20% of the undiscovered oil and gas is probably on those continental shelves, Who owns the Arctic is now a really important question. There's also impacts on tourism. The Russian icebreaker 50 Years of Victory makes 5 round trips to the North Pole every summer, taking 120 tourists on the most powerful icebreaker in the world. It's nuclear powered, it's incredible. But at the same time, a cruise ship, the Crystal Serenity, did the Northwest Passage. It's great that there are these opportunities, but what if something goes wrong? There's also impacts on ecosystems, impacts we really don't understand. We don't know what's going to be the consequences of changing the timing of algal blooms and phytoplankton blooms. And there's a real concern that the impacts will be strongly negative on the large mammals of the Arctic. And finally, there's the issue of what happens in the Arctic may not stay in the Arctic. There's a lot of research going on now to investigate whether or not there are connections to the changes that we're seeing in the Arctic in mid-latitude weather patterns. And this also motivates us for Mosaic, that we know the observations we were making hopefully will make a difference and have a beneficial impact on people. Thank you.
For questions, and we have a microphone that we ask you.
I can probably just shout. Oh. We'll have about 20 questions, but we'll start with one. Is anyone suspecting or it seemed from what you showed there is a Pacific to Atlantic flow of water through the Arctic Ocean, up through the Bering Strait, ultimately then comes out down the coast of Greenland, right?
Not necessarily the water. If you look at the large-scale pattern of ice drift, there's a number of components. There's the Beaufort jar, which kind of goes around in a circle like this, and then there's the transpolar drift that comes out that way. There's water that comes in through the Bering Strait, and by nature it's fairly shallow because the Bering Strait is shallow, and that tends to branch off this way. And there's also water that comes in, deeper water from the North Atlantic that comes in this way. There are these maps of ocean currents, and we could spend all day trying to figure them out.
Well, the essence of my question, the essence of my question really is anyone suggesting that the changes in the polar ice that are clearly happening may change really global ocean circulation patterns, starting with those in the Arctic and then a kind of chain reaction through the rest of the ocean?
I think for sea ice, I mean, it is a source of fresh water when it melts. And I think in general, there's always been interest. Let's go back to there's always been the question of shutting down the circulation. And I think the consensus is that melting sea ice isn't enough to do that. You have to have bad things happen to Greenland to get enough fresh water. Did the Greenland people think that's?
Were there any Indigenous people involved in the planning, and are there any on the ship that are involved in doing the research?
I don't know. I don't know if there's any on the ship now. And I don't know. There may have been a small presence in the planning. And I know for the work that I've been involved with recently north of Alaska, like from the Healy, there's always been Indigenous observers on board. And also, we've always kind of gone around and informed the communities what we're doing and what we hope to learn, and then got back to say, here's what we did learn. For this, I'm not so sure about it, and maybe because it's so far north. But I don't know. I'll check into that.
Have you used some of the information you've gathered on the previous lock-ins, and how do you transpose or apply it to this Mosaic process?
Yeah, there's, I mean, I was involved with the Sheba program, which was another year-long drift in 97 and 98 in a different neighborhood off of here. So there are some things that you can transfer. There was also a Norwegian experiment over in this area. There was a 6-month experiment. So I think there are logistic things that you can transfer. There are scientific things, but one of the things scientifically that's been a challenge is a large part of the motivation for Mosaic is we're in the new Arctic. So in terms of, with Sheba, when we were picking a flow, one of the concerns was don't get something too thick. That's not a problem with Mosaic. So there are lessons learned we can transfer, but there's a lot of big unknowns. Another big unknown is how much snow we're going to have. You know, over in this part of the Arctic, well, the old joke, at least it's my old joke, that for snow, the answer is 0.3. The snow depth is 0.3 meters. The snow density is 0.3 kilograms per meter, or grams per cubic centimeter, and the conductivity is 0.3. That may not apply over here.
So you don't have that information where it should.
Right. Yeah. And that was part of the reason to do it over there. Well, there were a couple reasons to do it over there, and one was we hadn't done a year-long drift experiment over there.
Is there any data to show the difference in temperatures and in ice melts between the Arctic and Antarctica?
Yes. And if I drew that same kind of plot for the Antarctic, is this, it would look a lot different. In general, the Antarctic went through a period where the sea ice cover was not declining, maybe increasing slightly overall, and now it's reached a point where it's starting to slightly decline. But it does look a lot different. And I think that they're aptly named. They're the Arctic and the anti-Arctic. You've got an ocean surrounded by continents, and then a continent surrounded by ocean. And in the Antarctic, I think that ocean boundary plays a much larger role.
You mentioned the earlier Sheba experiment. Could you just give an overview as to what Sheba didn't do that you need to do now and other contrasts between the two experiments?
Sure. You probably don't want to get me started on Sheba. But since it's October 2nd, on October 2nd, 1997, the engines of the Grossier were shut down, starting the drift of Ice Station Sheba. A couple of the big differences is Sheba, the focus was on understanding the ice-albedo feedback and the cloud radiation feedback, and then using that understanding to improve models. Whereas Mosaic, it's to determine whether the causes and consequences of an ice-diminished Arctic. So the basic science question is different. Another major difference is that Sheba was focused on atmosphere, ice, and ocean. Mosaic is also interested in those three components, but adds ecosystems and biogeochemistry, because we've really come to realize that during Sheba, we were just beginning to understand the Arctic was a system. Well, we were beginning to understand it was a physical system. And now we understand that that physical system is tightly connected to biogeochemistry and ecosystems as well. And then there are other things, like there's one of the things with Mosaic for the clouds, there are techniques now to look at aerosols that just didn't exist during Sheba. And some of these terrestrial lidars we'll be using to map, the surface. So there's new tools as well. I will say that early on in the 10 years of planning, it took some effort to dissuade people that, oh, another Sheba. But we finally did it.
One more question in the back.
Could you explain why the changes affecting Earth overall, they're so much more extreme in the Arctic than in the Antarctic?
I'll talk about the Arctic first. And that's, we have this floating ice cover, and as I mentioned earlier, it's bright and it's white. It's highly reflective. But as that melts, it exposes the dark ocean. And you get this ice-albedo feedback, which in the models is manifested as polar amplification. I think the difference in the Antarctic, and there are Antarctic people that can probably answer this better than I can, is that you've got this giant block of ice there that's a couple miles high, and it's going to take a lot to change that. Does that sound right?
All right, well,
Okay, I have another thing to say. To respond to you, that we talked about the 3 rules of the Arctic. Rule number 3 was never run, never sweat. Rule number 2 was always have a ticket home. And rule number 1, and the most important rule, was eat as much as you can whenever you can, which should segue into the reception.